Hello everyone, welcome back to our PySpark interview series. In today's video, we'll be answering a fundamental question: what is an RDDD in PySpark? If you're new to PySpark or preparing for interviews, understanding RDDs is crucial. They are the backbone of distributed data processing in PySpark, enabling efficient handling of big data. Stick around as we break down the core concepts of RDDs, their key features, and why they are essential for large scale data processing. Introduction. An RDD Resilient Distributed Dataset is the core data structure in both PySpark and Apache Spark, designed to handle large-scale distributed data processing efficiently. An RDD represents an immutable collection of objects distributed across multiple nodes in a cluster. This means that once an RDD is created, it cannot be changed, but you can apply transformations to generate new RDs. The immutability and distributed nature of RDDs allows Spark to handle data in parallel, processing different parts of the dataset on different nodes simultaneously, which significantly improves performance. RDs are designed to be fault tolerant, meaning that if any node in the cluster fails, Spark can automatically recover the lost data by recomputing it based on the original RDD's lineage, a record of the transformations applied to the dataset. This feature ensures reliability and robustness even in environments where hardware failures or network issues may occur. RDDs are the foundational building blocks of Spark's distributed computing framework, enabling scalable and efficient data processing across clusters. The key features of RDD, Resilient Distributed Dataset. 1. Immutable RDDs are immutable, meaning once they are created, they cannot be modified. Instead of changing the original RDD, PySpark applies transformations to generate new RDDs. This immutability ensures consistency and reliability in distributed computing as the original dataset remains unchanged, making it easier to track the transformations and recover data if necessary. 2. Distributed the data within an RDD is distributed across multiple nodes in a cluster. RDDs are split into partitions, with each partition being processed on different worker nodes in parallel. This distribution enables PySpark to process large datasets efficiently by taking advantage of the computational power of multiple machines, significantly speeding up data processing tasks. 3. Fault-tolerant RDDs are designed to be fault-tolerant, meaning they can automatically recover from node failures. Spark maintains lineage information, which is the record of all the transformations applied to an RDD. If a node goes down, Spark can recompute only the lost partitions by reapplying the transformations from the original data source, ensuring the job continues without data loss. 4. Lazy evaluation transformations in PySpark are evaluated lazily, meaning they do not trigger execution immediately. Instead, PySpark builds a directed acyclic graph DAG that represents the sequence of transformations and waits for an action like collect or count to be called before executing the computation. This lazy evaluation allows PySpark to optimize the execution plan and minimize unnecessary calculations. 5. Partitioning RDDs support partitioning, where data is divided into smaller, independent chunks called partitions. This allows for parallel processing, as each partition can be processed by separate executors on different nodes. Partitioning plays a key role in performance optimization, enabling Spark to handle massive datasets more efficiently and in parallel. 6. Transformations. RDDs support transformations, which are operations like map, filter, and flat map that define how the data should be processed. Transformations are lazy operations, meaning they return new RDDs without actually performing any computation. The computation is deferred until an action is called, allowing Spark to optimize the workflow. 7. Actions in PySpark, such as collect, count, or save a text file, trigger the actual execution of the transformations applied to the RDD. When an action is called, Spark executes the entire computation as defined by the DAG and returns the final result. actions are necessary to obtain outputs or save the results of computations. Practical examples. 1. Create RDD from a Python list using parallelize. This simple PySpark code demonstrates the creation of an RDD resilient distributed dataset from a basic Python list and how to retrieve the data using the collect action. First, the data is defined as a list 1, 2, 3, 4, 5. Using sc.parallelize data, the list is converted into an RDD, which distributes the data across multiple partitions. The function parallelize is commonly used to create RDDs from Python objects and automatically splits the data into partitions based on the cluster's configuration. This partitioning allows for parallel processing in a distributed environment where each partition can be processed independently by different worker nodes. The collect action is then applied to the RDD. Collect is an action that triggers the execution of the transformations, if any, and retrieves the data from the distributed RDDD back to the driver program. Since there are no transformations applied in this case, collect simply gathers the original list of numbers and returns them as a Python list. The result is printed as 1, 2, 3, 4, 5, showing the complete data in the RDD. This example highlights the basic process of creating an RDD, distributing data across a cluster and retrieving the results using an action. 2. Create RDDD from an external file text file. This PySpark example demonstrates how to create an RDDD resilient distributed dataset by reading data from a text file, followed by retrieving and printing a portion of the file using the take action. The text file myfile.txt contains several lines of text related to PySpark, such as PySpark is a distributed data processing framework and RDD is a core abstraction in PySpark. The code uses sc.textfile to read the file and create an RDD, where each line in the text file is treated as a separate element in the RDD. The sc.textfile function is a common way to load external data into Spark for further processing, especially when dealing with text files. Once the RDD is created from the text file, the take5 action is applied. Take is an action that retrieves a specified number of elements from the RDDD, in this case the first 5 lines of the file. Like other actions in PySpark, take triggers the execution of any transformations and returns the result to the driver program. The result, which contains the first 5 lines of the text file, is printed as a list of strings. Each line from the file is returned as a separate string in the list. The output demonstrates how PySpark reads external files and processes them in a distributed manner. The file is split into partitions depending on the cluster configuration, and each partition can be processed by different worker nodes in parallel, enabling efficient handling of large data sets. This example shows the basic process of loading data from a file, creating an RDDD, and using the take action to inspect part of the data. It highlights the simplicity of working with external files in PySpark while benefiting from distributed computing. 3. Create RDDD from a directory of files. This PySpark example demonstrates how to create an RDD from multiple text files within a directory and perform an action to count the total number of lines across all the files. The directory path to directory contains 3 text files, file1.txt, file2.txt, and file3.txt. Each file has a different number of lines, with file1.txt containing 2 lines, file2.txt containing 3 lines, and file3.txt containing 1 line. The goal is to load all the files into an RDD and count the total number of lines across the 3 files. Using the sc.textfile function, PySpark reads all the text files in the specified directory by using the wildcard character, which matches all files. The textfile function creates an RDD where each line in the files is treated as an element in the RDD. This approach allows Spark to handle multiple files simultaneously, distributing them across the cluster for parallel processing. After creating the RDD, the count action is applied. Count is an action that triggers the execution of any transformations and returns the total number of elements in the RDD. In this case, the elements are the lines from all the text files. So count returns the total number of lines across all three files. The result 6 is printed, indicating that the total number of lines in the directory is 6. This result includes 2 lines from file1.txt, 3 lines from file2.txt, and 1 line from file3.txt. The example demonstrates how PySpark can efficiently read and process multiple files from a directory in parallel, distributing the data across the cluster to handle large datasets seamlessly. The use of the wildcard character in sc.txt file makes it convenient to process entire directories of files in a single step. 4. Create RDDD from a CSV file. In this PySpark example, we demonstrate how to read a CSV file and process its contents using RDDs. The CSV file mydata.csv contains information about individuals, including their names, ages, and cities. PySpark uses the sc.txt file function to load the file, where each line of the CSV file is treated as a string and becomes an element in the RDD. Once the RDD is created, a map transformation is applied to split each line by commas, converting the rows into lists of individual values columns such as name, age, city. This transformation allows us to break the structured data into manageable parts for further processing. After applying the transformation, the take 5 action is used to collect and return the first 5 rows, including the header and the first 4 rows of data. The output shows each row split into its respective columns, with each line of the CSV now represented as a list of values. This approach demonstrates how PySpark can efficiently load and process CSV files by reading the data into an RDD and using simple transformations to prepare it for further analysis or manipulation, all while leveraging distributed computing for scalability. 5. Create RDDD from a sequence of tuples. In this PySpark example, we create an RDDD from a list of tuples using the sc.parallelize function. The dataset consists of a list of tuples where each tuple contains a person's name and their corresponding age. The data is structured as follows: Alice 34, Bob 45, and Catherine 29. The sc.parallelize function distributes the list across multiple partitions within the Spark cluster, enabling parallel processing. This function is a common way to create an RDDD from in-memory data, allowing PySpark to distribute the data across multiple worker nodes for efficient processing. After creating the RDD, the collect action is used to gather all the elements of the RDD and return them to the driver program as a Python list. The collect action triggers the execution of the RDD transformations and actions, ensuring that all partitions are processed and the data is aggregated back to the driver node. Finally, the result is printed displaying the original list of tuples: Alice 34, Bob 45, Catherine 29. This example demonstrates the basic process of creating an RDD from in-memory data, distributing it across the cluster, and retrieving the results using the collect action, highlighting PySpark's ability to handle parallel processing of distributed data. 6. Create RDD from JSON files. In this PySpark example, we demonstrate how to read and process a JSON file using RDDs. The file mydata.json contains several JSON objects, each representing a person with their name, age, and city. The goal is to read this file into an RDD and pass the JSON data into Python dictionaries for further processing. The sc.text file function is used to read the JSON file, where each line in the file is treated as a separate element in the resulting RDD. This function loads the data from the specified path and creates an RDD where each element is a JSON string. To convert these JSON strings into Python dictionaries, we apply a map transformation using the json.loads function. This transformation processes each line of the RDD, converting the JSON string into a Python dictionary. As a result, each element in the RDD becomes a dictionary with key value pairs representing the fields from the original JSON objects, e.g., name Alice, age 30, city New York. Finally, the take 5 action is applied to retrieve the first 5 elements from the RDD, which are printed as a list of dictionaries. The output includes the past JSON objects from the file, showing that each line has been successfully converted into a Python dictionary. This example demonstrates how PySpark can handle JSON data, reading it from a file, parsing it, and preparing it for further analysis using RDD transformations and actions. 7. Create RDD from a list of dictionaries. In this PySpark example, we create an RDD from a list of Python dictionaries using the sc.parallelize function. The dataset consists of a list of dictionaries, where each dictionary represents a person with two fields, name and age. The data is structured as follows: name Alice, age 34, name Bob, age 45, and name Catherine, age 29. By using the scc.parallelize function, the list is distributed across multiple partitions, allowing PySpark to process the data in parallel across the cluster. This function is commonly used to create RDDs from in-memory collections, distributing the data across the available worker nodes for efficient distributed computation. Once the RDD is created, the collect action is used to retrieve all elements from the RDD and bring them back to the driver program as a Python list. The collect action triggers the execution of the RDD transformations and actions, ensuring that all partitions are processed and combined. After collecting the data, the output is printed, showing the original list of dictionaries: name Alice, age 34, name Bob, age 45, name Catherine, age 29. This example demonstrates how PySpark can handle structured data such as dictionaries and distribute it across a cluster for parallel processing. The parallelize function helps in creating RDDs from in-memory data, and the collect action retrieves the results for further analysis or display. And that wraps up our explanation of what is an RDD in PySpark. I hope this video gave you a clear understanding of how RDDs work and why they are so important in distributed computing. If you found this video helpful, don't forget to hit the like button, subscribe to the channel, and turn on the notification bell for more PySpark content. Thanks for watching and see you in the next video.